Well, hello there. We start off with our last chapter of section C, that is correlation analysis. And to begin with, what is correlation analysis? So, that is something which we will eventually answer. Now, what we are trying to do? We are trying to work with the bivariate data. Now, what is a bivariate data? Bivariate data means any data which consists two different variables. So one is x, another one is y. So x is one of the variable and y is another variable, and these are all the data values that which we have collected as an observation. So these are all the sample data values. Now, if we have collected this particular set of data and if we try to plot them on the coordinate axis, because obviously I have two set of data, so I can consider one on the x-axis, the other on the y-axis, and I can always plot them on the 2D plane. Now, if we plot it, what happens? We can get several different kinds of figure. I mean, several different kind of scenarios. So, of which there are three scenarios which we need to talk about. The first one is a scenario where all the data values are such that if I consider this x1, y1 as one coordinate, like x1 comma y1, like this, if I consider one coordinate and I plot it, then if I can see that the data values are plotted in such a way that if I draw a straight line, which is also called the regression line, but I am not using the term regression here, but any straight line which follows the trend of the plot. So you can see the data values are plotted in such a way, if I draw a straight line, the straight line would look something like this, right? The straight line need not be passing through origin, it can be anywhere, but the trend says that the straight line will go something like this. So if I have a straight line following the trend going like this, then we can see that this straight line has got a positive slope. So that means what? I can say, as this straight line has a positive slope, I can say that these two particular variables are positively correlated. So that's where the word correlation comes. So the basically it means that how well the data, I mean both the data, that is one variable, the other variable, goes well with each other. If I say that they are positively correlated, that means both the data go pretty well with each other. Then the other case where the data values are plotted in such a way that if I just draw a straight line following the trend, the straight line will be something like this, and I can see that the slope is negative. So in that case, if the slope is negative, that means we say that the data values are negatively correlated, and that means that both the data doesn't go with each other well. Then there can be a third case. Now here, the data values, once after plotting, they are so scattered that we actually cannot find a particular trend. Find a particular trend means here I can see that the data values have a particular trend. How to understand that trend? By drawing the straight line following that trend. The trend will be such that you can actually plot a straight line following the trend of the points plotted. In this case also, I can draw a straight line following the trend of the points plotted, but in this case I cannot. So therefore, here I say that these two data are not correlated to each other. Neither positively correlated nor negatively correlated. I would say that the data are not correlated with each other. Now, the idea of correlation is measured through something called a correlation coefficient. And this correlation coefficient is denoted by a small r or a Greek letter rho. This is the Greek letter rho. So this is the Greek letter. You can use any of the two, whichever you want. So before we go on finding the correlation coefficient, First, we need to understand what is covariance. Now, what is covariance? Covariance, by the definition of covariance, now you are not much bothered with the definition because all you need to remember is the formula. So, covariance is basically the mean of the product of the mean deviation of x and y. Now, we have already done mean deviation in the statistics part, that is the compulsory part. So, if you just follow from there, you will be remembering what is mean deviation. So all we require to do is find the mean, then subtract it from all the data values and then take the sum of it and then divide it by the total number of observations. So here what I do, I find the mean deviation of one variable, I find the mean deviation of the second variable, multiply their values, take the sum and then divide by the total number of data. So this is one formula, and if I multiply these two, I get this other formula. Fine. So these are the two formulas that you have. And now if you do a scale change in the sense, if I have say u, that is equals to x minus a by h, and v, that is equals to y minus b by k, if we have something like this, then the covariance of uv will be covariance of xy will be h into k times covariance of xy. So if you get a situation where the data values are such very big that you are finding it very difficult to calculate this figure, then you can always scale down the values. This a is called the assumed mean, this h is called the scaling factor. We all know that, the state deviation method that we have done. Similarly, b and k doing the same thing for y, and if you scale down the values and then calculate the covariance, all you need to do is just multiply the scaling factor back. You will get the original covariance. Fine. So covariance is just a value which is helpful to find actual correlation coefficient. So we are coming to that. So before we go to correlation coefficient, let us first solve few problems on covariance, and then we will be going to the problems of correlation coefficient. We'll understand it first, then we'll go to the problems. We start off with the first problem. Now, in the first problem we have find the covariance of xy between where the sum of x is given 50, sum of y is given 30, sum of xy is given minus 115, and the number of observation, that is n, is given 10. So all we need to do is just put everything into the formula and calculate. So the formula of covariance, as we did, is this: 1 by n summation xy minus 1 by n summation x summation y. So let us put all the values together and calculate. So therefore the covariance is minus 26.5. Number 2, find covariance of the following data. So now the same question can come in this format where you won't be given the summation x, summation y, summation xy values directly. All we need to do is calculate from the table and then find out. So for this, all we need to do is make a table something like this, where we have to make a third column of xy. So what is xy? It is product of the individual values of x and y. So let us do it. This is what it comes, and then add it up column wise. So summation x will be sum of all the values in column x, summation y is similarly for column y, and summation xy for column xy. Now we have got the values we require, and then we all need to put the value So this is the formula. Let us put it and calculate, and very miraculously the value comes out to be 0. All right. Okay, so let us come back. Now, the correlation coefficient, there are two different kinds of correlation coefficient. One is the Karl Pearson's correlation coefficient, and another one is Spearman's rank correlation. Now, Spearman's rank correlation, obviously coefficient, that part is there. Now, Spearman's rank correlation has been omitted from the syllabus, so we are not doing this. But this is actually there in the full syllabus, which has been omitted. So we are just skipping this out. So we will just talk about Karl Pearson's correlation coefficient. So to begin with, so let me just, okay. So to begin with, this Karl Pearson's correlation coefficient is denoted by R or rho x comma y to be precise. That's how we write it. And this is basically the covariance of x comma y divided by the standard deviation of x times the standard deviation of y. So that is the formula for finding the correlation coefficient. Now obviously, as we are not doing two types of correlation coefficient, so by the word correlation coefficient I always mean Karl Pearson's correlation coefficient. So this is the formula. Now just let us put it back all together. So if I put it back all together, what is covariance? Now covariance is summation, there is a 1 by n, summation xy minus 1 by n, summation x, summation y. Fine. Now that outside 1 by n will actually get cancelled. Why? Because there is 1 by n here, there is 1 by n here, under root 1 by n rather. So both that are under root 1 by n multiplied to give you 1 by n, which gets cancelled. Now if you just remember your compulsory statistics part, and there we have studied the formula for finding standard deviation. So let us go back there. So what is standard deviation? It is square root of the variance, and variance is summation x square minus summation x whole square by n. Obviously, whole by n, that comes out as 1 by root n here, and in another one gets multiplied. Here also, summation y square minus summation y whole square by n. So seems like a room full of formula, but once you just find all these values like summation xy, summation x, summation y, which we already know how to do it, so just put the values and calculate. So you have a calculator, not a problem. Now if I do a scale change, what happens? So if I have u that is equals to x minus a by h, and v that is equals to y minus b by k, where a and b are assumed means, h and k are scales. So in case of if I do this scaling here, in that case what happens? You see, covariance in itself requires a scaling factor of h and k. In case of standard deviation, here also I need a scaling factor of h, here also a scaling factor of k. So all those things will get cancelled actually, and that is the reason why Even if I do the scale, I mean, if I change the variables, then also the value of r remains the same. So if I do this, then let me just name this as r x comma, okay, so it's better to use rho xy just to give you the perspective. So even after changing the scale, rho xy will be equals to rho uv. So after changing the variables, whatever the correlation coefficient you get with the new variables, that is the same as the correlation coefficient for the actual variable. Okay. Now, few things to note. That is, the first thing, this value of this correlation coefficient ranges from -1 to 1. Okay. If it is 1, then we say it is strongly correlated, strongly positively correlated. If it is -1, then it is strongly negatively correlated. And if it is 0, then we say it is not correlated at all. And any value in between, if it is positive, then we say it is moderately correlated, fairly correlated, weakly correlated. So we use different adjectives for it. So if the value of r is near to 0, positive but near to 0, we say weakly correlated, weakly positively correlated. If it is negative and near to 0, weakly negatively correlated. So all these different words, fancy words we use. Fine. So that's it. That is it. This is the theory part for the chapter. Now let us move back to problems and solve few problems and understand how we need to apply this formula in the problem. So all we need to do is remember them. Fine. So let's do it. Question number 3. If the value of n is given 10, summation of x given 26, summation of y minus 27, summation of x squared 226, summation of y squared 267, and summation xy 7, find the correlation coefficient. Fine. So all we need to do, put it into the formula. This is the formula. It looks very scary, but all you need to do is do the calculation very carefully. So let us put all the values, and obviously let your calculator do the rest of the thing, and the value comes out to be 0.4403. You can just round it off to 2-digit, that is 0.44. Same question, a bit different way it is given. So the value of n is given 15, summation of x is given 375, summation of y given 270, summation of x minus x bar whole square is given 136, summation y minus y bar whole square is given 138, and the summation of the product of their deviation given 122. Find the correlation coefficient. So here, as we can see, we have to make use of a different formula, right? So what is the different formula? So first remember, what is the formula of correlation coefficient? Correlation coefficient is basically covariance of xy divided by the standard deviation of x times standard deviation of y. So all I need to do is find the standard deviation covariance individually and put it into the formula. So if we go back to the covariance, so the covariance formula was actually, from definition, it was the mean of product of the mean deviation. So mean of the sum of the product of the mean deviation. So by that definition, this is covariance. Now I would suggest you do not calculate at this stage. We can do our calculation after we have found out everything together. Then what is sigma x? That is the standard deviation of x, that is summation of x minus x bar whole square by n. That value is also given, so let us keep it like this. So under root 136 by 15. So let us keep it like that. Similarly, sigma y, that is the standard deviation of y, following the same formula is this. So now we are at a stage to calculate the correlation coefficient. So that is R equals to cov xy by sigma x sigma y. So all the values have been found out. So let us just put it and let your calculator do the rest of it. So the value is 0.8905, right? So from here, there can be one extra added question. The added question being discuss the correlation between x and y. So you can write that x and y are strongly correlated, strongly positively correlated, right? So because the value is almost near to 1, so therefore we can say that it is strongly correlated. Strong positive correlation, that also you can use. Now let us move to number 5. Now number 5 is the similar problem, but here we are not given the summation values directly. We have to calculate it. So this is a table given. From here I have to find the correlation coefficient. So we make a table like this with 5 different data: x, y, x square, y square and xy. Now I have made a horizontal table just to fit the whole thing in one place. You could have made a vertical table, which is the obvious choice. So it is completely up to you. So x square is this 36. It's just to do your calculation. I am just showing it: 36, 4, 16, 81. You know how to do it. Y square is square of all the values of y, and xy is product of x and y. Fine. Now you can see here the values have got a little bit bigger because x square, y square, when you are squaring, the values get bigger. So you could have actually scaled things down if you would have wanted. If not, you are okay with calculating big numbers, you can use this particular formula as well. You need not go on scaling things down. Now all I have to do, I have to add them up. So summation of x, that is all summation of all the values of x, that is 38. Summation of y is 94. Summation of x square is 236. Summation of y square 1160, and finally summation of xy 499. Now I got all the values that I required. So next job is to put it into this formula. So let us put it, and through the calculation we get that the value of the correlation coefficient is 0.9459. So that is suggesting that it has got a very strong correlation, right? So that's it. That is how we solve the problems of this chapter, more or less. There won't be any other kind of problem. Yes, there can be missing value problems. So like you are given the correlation coefficient and you may be given some missing data in the table. You have to find it. So go through the same process of finding all those summation x, summation y, summation x square, y square, all those values, and put it into the formula. It will give you an equation, and from there you will be able to solve it. Fine. So that's it. Thank you so much, and as always, if you have any doubt, get it clarified.